So now start video, share screen. All right. Yeah. So I hope all of you can see. Can you?
Yes, sir. We can see the screen.
Okay. So this is the last slide of the last class. And you may recall that we were in the process of looking at the recurrence and transience of unrestricted birth-death Markov chain on integers. So the state space is all positive, negative integers, of course, including 0, of course. And you may recall that this was, we had fixed some C and D such that C was less than D, strictly less than D. And psi y was defined as probability of reaching C, that is the left end point, before reaching D, if you start from the point Y, where Y can be between C and D. Of course, if the starting point itself is one of the endpoints, you already know this. Supposing psi at C is equal to 1 and psi at D equal to 0. So that act like some kind of a boundary values. So with the knowledge of those boundary values, we had to sort of determine the function. And in the last class, that is what we did. All this, using what is called the first step analysis. By the way, in the notes, all the plus signs have been inserted. And I didn't bother to do it in the slides. I mean, somebody had pointed out that was, yeah. So using the first step analysis means what happens in the very first step. So in the very first step, it starts from I, it can go to, because of the nature of this process, it can go to I+1 or I -1 or stay at I itself. And depending on those possibilities, we had, and also using the property of these things, intersection of events, and again the Markov property and so on, we got hold of this equation. And these things are known because these are the Pi, Qi, Ris. And by our definition of psi, these we know these are the function psi at I+1, I -1, and I itself. So using these things and by some elementary kind of arguments, we obtained something. And in this, we have used this symbol, capital theta x is equal to this. And that precisely you want what you find here. So this theta x stands for that ratio. Okay. So this is, if you have not noted it down, you may do so. Fine. So now what we do is we try to find rho yc for y strictly bigger than c. Recall that rho yc is the probability of reaching c in finite time starting from y. And of course, we are assuming y is strictly bigger than c. So, okay. So rho yc by definition is that, you don't recall that. So now notice that rho yc, while defining rho yc itself, we have noticed this. It is P sub y, that is if you start from y, Tc is the first hitting time of the point C, that is finite, the probability of that. So now that you can easily see that it is limit as d goes to infinity, that is the right point which we kept, that d, as it goes to infinity, P sub y, Tc strictly less than Td. And here, y is a point strictly greater than c and so on. Now look at this expression. So this is, yeah, look at this. It is limit d going to infinity of psi y. So in that case, this is infinite if this guy, what is found here, so that goes to, that probability will be 1 if this goes to infinity. If this goes to infinity, that also will go to infinity, and you can easily see that that ratio will be 1. You have seen such limits in your early basic calculus or analysis courses. And if this happens to be finite, then this one, for whatever may be the value of d, this will be strictly less than 1. Because since y is a point bigger than c, you will invariably have this one smaller than that. And there is a 1 plus that. So you can easily convince yourselves that this rho yc equal to 1 if the summation of theta x going from c plus 1 to infinity is infinite, and that rho yc is strictly less than 1 if the same sum is finite. Okay. Now the next step is here, ultimately, remember that we are interested in a criteria for recurrence and a criteria for transience in terms of the PIs and QIs and so on. So we make remember this capital theta, that its definition depends on C. Okay. So we would like to sort of remove that thing. In other words, we would like to have a criteria which will be sort of 1 to infinity or something like that. Of course, you might say that why you could have started with c equal to 0 or something like that. Yes, but we could have done that. Yes. But then in that process, we will not have got an expression for this, for an arbitrary c and d, which is less than, where c is less than d. Okay, now put capital lambda x equal to this ratio. The numerator is q1, q2 up to qx. The denominator is p1, p2, px. And x running from, 1, 2, etc. With that,
sir, can you go to the previous slide once again? Yeah. So in the second case, why it is less than 1 if sigma theta x is less than infinity?
This converges, right? If that converges, see this expression. This is denominator is 1 plus that limit it will be. Here it will be just that limit.
Okay.
And 1 is strictly bigger than 0.
Okay, got it. Fine.
Okay. So you can verify that if c plus 1 is negative, then this can be written as summation of this theta x from c plus 1 up to 0, and from 1 to infinity of theta x, you can easily check that it will be this. I mean, some elementary algebra is needed. Manipulation with that symbols appropriate. So that is if c plus 1 is less than or equal to 0. And similarly, if c plus 1 is strictly bigger than 0, once again, you can see that this is equal to this. Both these things, this verification does require some work. You have to take up paper and pencil and do this thing, manipulation properly. And in this case, proving that this equality is easier if you start from the first term on the right side. Okay. Okay. Now, remember that we are interested in the convergence or divergence of this guy, the left side here. And notice here, this is the sum of only finitely many terms. So it will be just a finite number. And here, note that this is the ratio of the product of only finitely many numbers. Of course, each of this in the numerator by our assumption on pi's and qi's, this is positive. So this is a finite number. So consequently, this converges if and only if this infinite sum converges, and vice versa. I mean, that is, if diverges and that diverges. And similarly here, this is only sum of finitely many terms. And this is the product of only finitely many positive numbers. Therefore, this guy diverges if and only if this one diverges. So, rho yc equal to 1 for all y greater than c, if and only if this goes to infinity. This sum is infinity. So now in this kind of criteria, there is no dependence on C. And of course, rho yc is strictly less than 1 for all y greater than c, if and only if that same series converges. Of course, note that here y has to be strictly bigger than c. Okay. Now we have taken care of how to deal with when the process comes I mean, you keep a point fixed and approaching it from the right. What about the left? For that, you notice that if we take the process defined by yn equal to minus xn for all n, that is also an unrestricted birth-death Markov chain. Only thing is the roles of P's and Q's are reversed. What you had earlier might have called head or tail will be called the other way around, tail and head. What you might have called success and failure, again, those things could get reversed. So instead of xn, you put yn in the above analysis. Therefore, rho yd for the original Markov chain, it will be something like that, some corresponding thing for approaching minus d or d from the left side. I mean, sorry, right side. Approaching d from the left side for the original Markov chain will be same thing as approaching from the right for the modified Markov chain, that is yn. Yeah. So using that, and instead of taking y greater than c, now you take y less than d. And a similar analysis gives you rho yd is equal to 1 for all this rho y and all, now it is in terms of the original Markov chain. Is same thing as the sum x going from upward minus infinity to 0 of px plus 1 p0 and divided by this. That is diverging that series, and correspondingly the rho yd is strictly less than 1 for all y less than d if.
Sir,
yeah,
how can x go from minus infinity to 0? Shouldn't it have been x going from 0 to minus infinity?
Well, that is a matter of notation, right?
Okay.
It is just that all the terms involved are between minus infinity to 0. Don't you write the interval minus infinity to 0? Of course, for calculating or checking and things like that, you have to say that thing as, let us say, P0, P minus 1, and P minus 2 up to P minus 10, and so divided by Q of those things, and 10, 11, and things like that. Minus 10, minus 11, and so on. This is just to emphasize that in the original, this thing, that all the negative numbers are also included. You write, for example, integral minus infinity to 0, right? If you are comfortable with that, why not with this? All your gamma integral and various things, it's not the gamma integral, that's on the positive side. Let's say the normal, the distribution function of this normal random variable and things like that, when you write, you start from minus infinity to x. After all, integration is a kind of, abstraction of the process of summation. Okay. So we have taken care of rho. For example, if you take C, that C equal to D equal to 0 or something like that, rho Y0, when Y is strictly bigger than 0, and also you have taken care of rho Y0 when Y is strictly less than 0. What about, but you remember our notion of transience recurrence depends on rho YY equal to 1 or strictly less than 1 for any Y. Of course, this we have seen that this Markov chain is irreducible. So if there is one recurrent state, the whole chain is recurrent. And similarly, if there is one transient state, the whole chain is transient. Okay. Now, use an argument similar to what we had done much earlier. That dagger. Where is that guy dagger? Let us. Yeah. We had got an expression for psi at I in terms of psi at I plus 1 and I minus 1. And of course, psi A itself. So go through a first step analysis in this fashion. If you do that, yeah, you will get rho YY equal to RY plus P sub Y rho Y1 to Y, Q sub Y rho Y1 to Y minus 1 to Y. Okay. Now notice that if we want rho YY to be equal to 1, we should have that rho Y1 Y as well as rho Y minus 1, sorry, rho Y plus 1 Y as well as rho Y minus 1 Y, both of them have to be 1. Then you will get Py plus Qy plus Ry equal to 1. So even if one of them fails to be 1, you will not get rho YY equal to 1. And remember that here we have, this has to be infinity for this to happen for all Y less than D. And similarly, for Y greater than C, we want this to be equal to infinity. Now suppose this holds as well as this holds. So if this holds, then using that, you will get rho Y plus 1. Y plus 1 is strictly bigger than 0. Or rather, strictly bigger than Y. This will be equal to 1 if this happens. And if this happens, rho Y minus 1 Y will be equal to. Consequently, by that equation star, which we saw in the preceding slide, you will get rho YY equal to 1 for all. If at least one of these series is convergent, then correspondingly you will get rho Y plus 1 Y strictly less than 1, or the other one will be strictly less than. In either case, rho YY will be strictly less than 1 for all. So we have the theorem. If both these series, that is summation x going to infinity, q1, q2, qx divided by p1, p2, px is infinity. And also summation minus infinity to 0. I mean, for convenience, we read it this way. We can even also read other way. P0, P minus 1, etc. up to Px divided by Q0, Q at minus 1, Q at minus 2. That thing is equal to infinity. So that, if that converges to, or rather diverges, then the unrestricted birth-death Markov chain is recurrent. If at least one of the series is convergent, then the Markov chain is transient. Yeah. Note it down if you want to. So now we can say something about the one-dimensional simple random walk. You know that is a unrestricted birth-death Markov chain, where all the PIs are the same and all the QIs are the same. So the unrestricted, simple unrestricted random walk on Z is recurrent only in the symmetric case, if and only if P is equal to Q is equal to half. In all the other cases, the random walk is transient. Okay. So now let us look at another birth-death Markov chain with one absorbing boundary. So in this case, the state space is 0, 1, 2, etc. All non-negative integers. And 0 is the absorbing boundary. So since 0 is the absorbing boundary, P sub 0, 0 equal to 1. And if 0 is the starting point, you cannot go anywhere else. So P sub 0j is 0 for j greater than or equal. And for I greater than or equal to 1, it is just like the unrestricted case. P sub I plus 1 is Pi, P sub I minus 1 is Qi, Pii is Ri. And both the Pi's and Qis are strictly positive. Ri can possibly be 0, but Pi plus Qi plus Ri should sum up to 1 for all. Okay, please note it down. I think you would have already seen this earlier.
So this Markov chain is not irreducible.
This Markov chain, you have rightly observed, it is not irreducible. Yes. Good. So for any strictly positive y, note that the probability of reaching 0 starting from y is a strictly positive number. So probability of reaching 0 from y in finite number of steps. That probability is rho y0. That would be certainly greater than or equal to, in the very first step, from q to, y to y minus 1 we come. So that probability is this, and so on and so forth. And finally, from the yth step, 1 to 0. So it is a product of these numbers. This is a strictly positive number because all the Qis are positive. So rho y0 is strictly positive. In other words, starting from any y strictly positive, you can, 0 is accessible from y. So 0 is accessible from y. So from y you can reach 0 in finite number of steps with positive probability. However, rho 0y is 0 for all y greater than or equal to 1. Consequently, rho yy is strictly less than for any y greater than or equal to 1. So which means any y greater than or equal to 1 is a transient state. Please note it down. Okay. So since P00 is 1, that is y is an absorbing state, any absorbing state is clearly a recurrent state. So as one of you observed, this Markov chain is not irreducible. So we have the following result. So this Markov chain is not irreducible. That's the first observation. The state 0 is absorbing, hence it is recurrent. All non-zero states are transient. So in this case, the state space S can be decomposed into these two disjoint units, S sub T union S sub R. And S sub R is just the singleton set. And S sub T is 1, 2, 3, etc. Okay. So now in this case, note that there are infinitely many transient states. I think I will stop here for the day because the next thing is we will consider the reflecting boundary. That we will take it up in the next class. By the way, those of you who came late, there were before some of you came, some queries were raised as to the portion for the midterm exam. When I reach that stage, when I finish that this thing, I will make the announcement. However, after that the portion is finished, till the mid-semester exam, classes will generally go on and some material will be covered.
So is today's lecture over?
Today's lecture is over. I'm waiting for you to, if you want to copy down something or not, so that after once you are through, if you give the green signal, I can stop sharing and then end the session.
Sir, what is C1 here?
C sub 1 is that, remember that when we, that decomposition when we studied of the state space, the irreducible recurrent classes we had denoted by C1, C2, etc., right?
Oh, right. Okay. Thanks.
Corresponding to that. So here there is only one recurrent state, and that by itself forms a irreducible class, because if you start from 0, you cannot go anywhere else. See here, right? 0 is an absorbing state. So once you fall into that, you are, the process is done.
Yeah, okay, got it. Thanks. I was just confused about the notation.
Yeah. So the sort of this notation goes back to that decomposition. Yeah, some such things hereafter it might be, yeah, but it is good that you raised this query, because what is suddenly a C1 is cropping up. Yes.
So sir, what will you do in the next class?
Birthlet chain with reflecting boundary.
But that with deflecting boundary. Okay.
So that's a kind of sneaking preview of what things to come. But you will see the picture only next time. Okay, I'll stop sharing. And if you don't have any queries, okay, take care. And we will see you on Friday.